As you remember, on Monday we started the physics with a lecture on physics list, and I was talking about particles, processes, physics list, constructors, electromagnetic options immediately. That was probably completely new. So now, before we finish everything, we get back a bit to this physics list story, and we will look it again, and hopefully now you will recognize much more things. It will make much more sense. And after this, we will try to give some guidelines how to choose your physics list for your application. Okay, we can give only guidelines because there is no recipe that you can follow from A to Z and it will be fine. Because each application is different. But there are some groups of similar activities at least, and so on and so on. And there are some tools or available websites that you can use. And I will try to show those things. So first, let's see very briefly what we were saying regarding the physics list. Okay, why we are talking about the physics list? Because physics list is the way in which you set up your physics environment, as it was mentioned. This is where you define all the particles that you want to use in your simulation, and you define all the physics processes, and you assign all the processes to your particle. Okay. Now, you can go back to lecture physics 1 lecture, and you will see all the details, as I mentioned, how you do it, and so on. The important thing is that if you need to give a physics list. Without giving a physics list, you cannot do simulation. On the same time, choosing your physics list means that you describe your physics environment. So when you choose the physics list, when you describe your physics environment, then usually it's necessary that you have an understanding, a detailed understanding of what kind of particles will play an important role and what kind of interactions will play an important role. If we go even further, then it's not enough to know what kind of interactions will play a role in the case of the application, but how accurately you need to describe the interactions. Because as I mentioned, Geant4 provides many different models to describe one interaction based on different approximation. And if you choose one that doesn't contain all the details that you need, then you will be in trouble. Or if you don't put some particles that plays a role in your application, then you will be in some trouble. It's same if you forget some important interactions, then your simulation will go through fine, your result will be plotted as printed out as a histogram or whatever you are computing, but it won't work. Okay, the result won't be good. We will see at the end how you can try to make sure that everything was set up properly. So you don't need to start from scratch, putting particles, few hundred there, and then defining few hundred times few processes, adding models to each, as I mentioned, because there are different level of details that you can start and put a physics list or choose a physics list. What is recommended actually is that you try to find one of the physics list that's available in the toolkit already, complete physics list. You try to see if one of them is suitable for you, for your application, as a starting point. Okay. As a starting point, because these physics lists were put together, I mentioned this, I'm just repeating now. These physics lists were put together for some specific applications or application areas. Now, these are stable because you can imagine Atlas and CMS means several thousand of users. So we need to make sure that they won't be upset. So they are stable, they are nice. well tested and well maintained. But I must say immediately that FT-FT-BERT is what they are based on, but this is where they start. Okay. None of them are using FT-FT-BERT as it is, as a physics list. They have different settings. They started from FT-FT-BERT, but they changed a bit. And they changed in a different way because their detector is different. So their need will be different. And this is true in your case as well. You pick up one of these, and you will need to make sure that you tailored this physics list to your special case, to your application. Now, what does it mean? It means that you need to validate, actually, for the physics list, either if you choose one of these, or if you start to put and change them, whatever, before you really start to do your simulation and you start to produce millions of events and so on, you need to make sure that this is fine. The physics list is appropriate to describe your physics environment. Now, just to remind you, when you see this predefined physics list, that you see the naming convention, that first the string models, then cascade, then as an option, you can use the HP underscore HP will refer to the high precision neutron model, and at the very end, if you have nothing, that means that you use the G4EM standard physics constructor, or you can put EMV, Y, Z, depending on how much level of accuracy you really want. But don't forget that when you choose a physics list, you always need to put two things. On one side, you choose that, okay, you want a really accurate description, but on the other side, we want to have a really efficient simulation, a fast simulation. So, in other words, you don't want to spend lots of time on computing things that doesn't play a role in your case, okay? Because then you waste lots of time instead of getting more and more statistics in your simulation. The more complex your simulation problem, the more time you will waste if you don't choose the optimal settings for your physics list. Now, regarding these options, and I showed this very nice way using the G4 Phys List Factory already on Monday, but now it makes more sense because you already tried it, I think, yesterday in the exercise, that you can use this Phys List Factory to obtain any of this reference physics list easily. Now, a general comment to this, that when you see somewhere you make a search on the web. This is I also recommend. Whenever you want to see how to do something in your application, you can try to search immediately on Google. Google will give you many things because there are many people using Geant4. Okay. So when you see something like you want to use this, or you see that somebody is using this G4 Phys List Factory, for example, and you would like to know what is it, then you go to your Geant4 source and you open this class. And if you open this, you will get first a better resolution than this. But you get many information within a second. Okay. You see immediately what kind of strings you can pass. You go a bit below, and you see what's happening when you pass a string. The proper physics list, depending on the name, will be created, and even further, as I mentioned, if you go back, that the electromagnetic option can be changed easily. for them. But for the first question, okay, you want to get a reference physics list. What reference physics lists are available? Yeah, there is the documentation, but when you are there and you are typing, within 1 second you can see immediately. And now, after this week, you know the meaning each of these substring. Okay, it's true for everything. It's not specific for the physics list. If you see something in the code starting with G4, something, a class, go there, open it, and see. Or you can use some documentation, or Dennis mentioned that even there are the oxygen documentation available, and you can see what are the methods that you can use, what are the functionalities that are provided, and so on and so on. So, what are the recommendations? Now, let's see a bit step by step. There are different scenarios. The first one is the optimal, which means that you can hardly see this case. When the user or users has a very good understanding, a very detailed understanding of the physics that they would like to simulate. On the same time, they have a very good understanding of the toolkit that they would like to use, for example, Geant4. That's the ideal situation, because in this case, at least one or few person knows very well what kind of particles, what kind of interactions plays an important role. In that case, even they know whether there are some low energy interactions need to be described with this precision or that precision, and they can put together a nice physics list. Of course, it almost never happens. Why? Because in many cases, it's not enough that somebody knows the electromagnetic part. Somebody should know, for example, even very well the low energy electromagnetic part. Or electromagnetic part is just the electromagnetic. What about the hadronic part? There are not too many people who understand very well from the electromagnetic down up to the hadronic physics, high energy, everything. But few of them can come together and they can start to put together the things. But even in this case, if they are the biggest expert in the field, before they start to use the simulation, it's very important that they need to validate the physics that they put together. It's kind of part of your simulation. When you write the development part, I mean. If you put together, if you describe your detector, fine. If you describe your primary generator, fine. If you put together some physics list, fine. You run your simulation, fine, it will be running. But you are still not ready to use your simulation. You need to make sure that what you will see as an output, it's appropriate. Nothing is missing. And in order to do this, you will go through this validation. We will get back to this validation in a second. Now, of course, you don't need to be a world expert in string models to decide whether some string models will be probably good for you or not, because in many cases you don't care about the string models. I can tell. Many of our users nothing about the string models, because they are working at low energy. Nothing happens like this. But others, yes. So what is the second scenario that works in many cases is that you know very well what you want to do. Your application, simulation application, belongs to a well-defined application area. Like the high energy physics, then you know that you are working with Atlas and so on, then immediately you target yourself into a direction. Or you are doing medical physics, you are doing some simulation regarding medical physics, you immediately shrink down the possibilities where you can look for physics list. And as I mentioned, the reference physics list that we saw before, they are put together not just because we thought that somebody might be happy to see this kind of physics list, because there were users. There are user communities that are using each of those physics lists. And if you go to the physics list lecture and you go to the documentation links that I put there, you will see that which physics list, predefined physics list, is used by which user community. So you can, with this, you can choose your reference physics list depending on your application area. And again, this is your starting point because you need to make sure that this physics list and the settings, which is another point, will be suitable in your case. When you take a physics list and particles are defined, processes, models are defined, and they are attached. Okay, this is the physics list. But beyond that, there are many, you will see, there are many things that you can change and tailor everything to your applications. I was talking about the production cuts, for example, but we will get back to this. So all these things belongs to making sure that everything is fine with your physics list. Now, if you don't know where you should go, where you should start, the one thing that works in many cases, but it's a bit time-consuming, is that you choose the most accurate physics settings that we provide. And you do a simulation with these most accurate physics settings. Okay, I told you that, for example, the EM option 4, the EMZ, contains everything that we can do in general with the standard and low energy electromagnetic description, with such settings that we cannot do better at the moment. So you take it, you run your simulation, and you will get a rough result, because of course you don't run it for 2 weeks, because you are still not ready, because you are still in the validation phase, you are still trying to put together your physics. You get some rough result. Then you go back and you choose the standard option. That will be probably significantly faster in your case. And you see how much your result is different. So you use the rough result that you obtain with the most accurate option as a kind of reference. And you see with the faster but less accurate option how far you are. And you can change and you can get closer to the most accurate, and you will see what are those components that are really playing role in your case to get accuracy. I mentioned we will see an example for this, for example. Now, as I mentioned, during the validation, what you need to do is that you actually choose your physics and you need to make sure that it describes what you want to really simulate. How you do this, you need to have some experimental data to see, some experimental data regarding your application. It's not exactly the experimental data, for example, that you want to simulate, because I would not call it modeling, because that's called fit. Okay. So you are using, in the ideal case, some independent data that are somehow related to your application area, and will tell something whether you are doing, I don't know, the proton interactions properly, or whether you do the electron transport simulation properly. And there are some databases or websites that you can use, because, of course, during the development phase, we are using many tests. You cannot imagine how many. to run our new development, and regularly we compare the simulation to experimental data. And you can see, you can go to the Geant4 website, the validation part, and so on to see some validation. You can go there, and you will find many different things. Now we will have a look to these new things, this Geant wall grid testing. I just would like to show how one validation plot looks like and what information it gives you. So this will be this Geant wall validation portal. Of course, you will see the whole screen if you go there, because we have the other part as well. And there are descriptions if you go there and so on. But I immediately will come and choose one test, okay? You see each of this line testing different things. You can see Bremsstrahlung, electron scattering, fluctuation test, and so on and so on. So we test each part, each block that we are using to build up our physics list. These are, for example, for the electromagnetic part. So how we do that? There are some less descriptive names like test 37, okay? There is a description. I mean, if each test has a description, then you see what is this test 37. Now, this website is under development, okay? There was a big progress last year, and this year it will be even better. So when time is going, the number of tests is just increasing, which means that you can see more and more diverse comparisons with experimental data. And no, it's a bit, okay, we don't have all the versions and so on, but it will come, and you will see even how some results are changing from version to version and so on. But let me choose only one version, the 10.5 version. And here in the physics list option, you can see this is an electromagnetic test, which means that the hadronic interaction doesn't play a role in this test. I will show soon what is this test. And you can see all these constructors that I was mentioning. You can see, you can recognize them. EM standard, option 0, 1, 2, 3, 4. So let's see and choose only two. The option 0, the standard, and the option 4. And let's put some experimental data. No, the simulation is not running now. Okay, when 10.5 was available, there were lots of simulation put into the database, and according to your query, now some plots will be generated. Now, in this case, what's happening is very simple. This test is testing how accurately we can describe electron transport, especially in the lower energy part, below 1 MeV. So we have a target which is hit by electrons from one side with a given energy. And each plot, for example, here you can see the target is aluminium, and each of these plot is the same experiment with different electron energy from 1 MeV going down. And the target in this case is aluminium, and the energy deposited by this electron, primary electron, as a function of the depth is simulated here. And there are experimental data. For each, or for most of them, there are experimental data. So what we can do all these simulations. We can choose the default electromagnetic option, like I did now, and the most accurate. And I want to see, for example, how well I can describe this experimental data with the most accurate one, and how far I will be with this accuracy if I choose the standard description. And if you come, you will see many plots. Let's choose one. Unfortunately, half of it missing. This is a 500 kilo electron volt electron coming in case of, I think, tantalum. And you can see the black dots. Those are the experimental data. The yellow one, if you go down, it's written down. The yellow one is EM standard option 4, and the blue one is EM standard. So, from this one plot, you can see that if you would like to simulate those energy deposition, then it's better if accuracy is important for you. It's option 0, the standard, is probably not the best choice for you. Because you will see from this data immediately, you can see here, this will be for uranium and so on. I think if you go down heavier and heavier targets, then the standard electromagnetic option will make bigger and bigger mistakes. While with option 4, the most accurate one, will describe always very nicely your experimental data, even in the case if you have some sandwich structure, like in this case, there are, I don't remember, like, what was it, aluminium, gold, aluminium. Okay, and the transport in this is also described very nicely. So I just wanted to show one example for this validation. As I mentioned, you can take option 4. You can make one simulation. This is the same story that we saw, just in the validation plot. In case of uranium, 1 MeV electron, beryllium, nearly 1 MeV electron energy deposit as a function of the depth. And you can see the red triangles are experimental data, and the black dots are the simulation. So with option 4, electromagnetic option 4, we describe very well the things. But practically taking the standard electromagnetic option and changing just the multiple Coulomb scattering model, adding few options, we can describe as good this experimental data as with option 4, but this simulation will be 20% faster because we don't do many more refined things here that we do on the same time with option 4. Okay, so you get a reference, you take a less accurate option, and you start to add the elements, and you see what's playing a role. And the final thing that, as I mentioned, when you choose a physics list, the list of particles, list of processes and models is one thing. You should always keep in mind that it can be even option 4, for example, for the electromagnetic description. If you set a wrong production threshold, then your result will be wrong. So there are settings that you cannot avoid to set because we don't know your particular geometry configuration. That can have, first of all, a significant effect to your simulation time, and a significant effect whether your simulation output will be correct or incorrect. That's it. Is there any question? So good luck to set up your physics list.
Okay, so this will be my final talk, except the closing remarks. And this Kernel 2 talk is how you wisely or cleverly, as you like, use Geant4. Okay? It has few, basically independent, 4 independent topics: user limit, attaching user information, and fast simulation, also known as the shower parameterization, and stacking mechanism. This final topic is my most favorite topic. Actually, I joined Geant4 collaboration because I wanted to have this, almost 30 years ago. Okay, so the user limit. So Geant4 has G4 user limit class. That is something you can use. It has 5 parameters. The first one is user step max, then track max, time max, kinetic energy max, and the range minimum. Sorry, this is minimum. So for this first one, max step, this is maximum step allowed. So if this is set, even if the volume boundary is far away, there is no physics going to happen. We limit the step as a maximum step length. Okay? And this makes quite a lot of sense if you have Cherenkov or scintillation detector, because typically scintillation detector is a very big space where if particle goes, basically this charged particle spits quite a bit of photons, right? So if you just naively let this particle go to the end, you end up with quite a huge number of optical photons. But instead, you may limit the step shortly and use the stacking mechanism I'm going to tell later. Just simulate these photons first. Then once you have done these photons, let parent particle go another step. This is a clever way to really minimize the number of particles in the memory. Okay? So this makes sense. So for Cherenkov or scintillation, that they generate optical photons. Okay? But in this case, it's a kind of artificial modification, so that in the end, instead of one step to the end, it may have 100 granular steps, but physics itself is not changing. The total number of optical photons generated along the full path won't change. So basically just a kind of artificial modifications. But for other cases, they really change things. Track maximum is, this is the length you allow to track to travel, okay? And maximum time, and in this case, how much, once particle travels this amount of time, it's killed. And this is actually used quite extensively in Atlas CMS, in particular Atlas. The issue is that once thermal neutron is created, it's floating around in the Atlas cavern forever, basically. And it takes quite an amount of CPU time to merely create any heat. Okay? So Atlas decided to kill neutron if it flies over, I don't remember, a few seconds or a few tens of seconds. Okay? That makes sense, because even if it generates heat, in 10 seconds, Atlas already have thousands or millions of beam crossing. So that doesn't make any sense. Okay? So, time max. Okay. And minimum kinetic energy domain, or minimum range domain, that is, as Dennis Mihari, in particular Mihari, and myself had already discussed, Geant4 tried to push particles until the complete stop. Okay? But if you want to compare Geant4 with MCNP, Fluka, eggs, whatever, they all have tracking cut. If particle comes to some threshold, actually particle is killed all of a sudden. Okay? And it stopped. We do one more effort. Okay? So if you want to compare Geant4 results with their result, we have to cheat the honest Geant4 simulation. That is, if particle comes down to certain energy, you have to kill it. Okay? You can set such user limit object to a logical volume or a region. The difference is the following. If you set it to the logical volume, this limit does not propagate to the daughter volumes. But if you set it to the region, all the volumes that belong to the region will see this limit. Okay? That is the difference. And in addition, if you use step max or max step, whatever, okay, you have to have a step limiter process in your physics list. Okay? If you don't have this, even if you set this step limit, step will not be limited. But this has an advantage because it's a physics process. You can assign this step limiter process only to some kind of particle. It's particle by particle, if you like. So you may want to kill only a neutron. Okay? In that sense, this killing it here. You may want to stop only a charged particle. So step limiter should be assigned only to the charged particle. So if you want to change the physics, that means limit to track, maximum track length, maximum time, or kinetic energy remaining, and so on and so forth. You have to have G4 user special cut process. And so let me repeat. This may set to any particular special kind of particle type, like neutron. Okay? So that only the neutron will be killed if it travels certain amount of time. Okay? Any question before I go forward? This particular topic is over now. Now, attaching user information to some Geant4 kernel classes. So, we have already actually examined by our hands-on. You touched upon G4 rank class. You have already had the hit class. This is something very similar. And trajectory point we have already discussed. In this case, we offer you a base class. You implement your own. So once you have your own rank class or hit class, that is your class. So you can put whatever the data members you like. Okay? That's it. It's simple. But for example, event track, we don't offer you any abstract base class. G4 event is always G4 event. I don't expect you to create your own event class. Track as well. But time to time, you want to keep some useful information for you associated with track class. Okay? But you are not allowed to create your track class derived from G4 track. But alternatively, we offer you G4V user track information abstract base class so that you can create your own your track information and you can associate it with G4 track. This is so-called aggregation, so that we don't have to have any partiality here, but you can still add an information to G4 track. Okay. So, for example, you may want to remember from which particle parent this particular track came from. It's very typical. In this case, when this secondary track is created, you create additional information of what is the parent and associate it with G4 track. That's it. Okay. And so on and so forth. So primary vertex, you may say, this comes from the glory Higgs detect particle or something, and so on and so forth. And region. But please note that, in particular for these four classes, for example, when G4 track is deleted at the end of the track, okay, associated information is also deleted. Okay? So before it is deleted, you have to copy it to something else. Okay? And the G4 user tracking action is the ideal location to do that. Trajectory we have already discussed. But if you want to have your own trajectory class, one thing you have to remember, please don't use G4 trajectory or G4 trajectory point concrete class as your base class, because they already have allocator somewhere. Because they use allocators, allocator works only for the concrete class. So if you naively add data member to G4 trajectory, it causes memory leak. And memory leak is really a killer. But instead, start from the abstract base class. And if you, once you have your own trajectory, here, it's a tracking action, tracking action is the place you put something. Here, if you, this track is a special condition. For example, it's not electron, positron, gamma, but an important particle like muon. Then say to the tracking manager, I'd like to store a trajectory. If it's a tiny electron, delta ray, you say, I don't want to store a trajectory. Okay? So you have already tried /tracking/store trajectory UI command, but it's applied to all the trajectories. But in this way, you can selectively, store the trajectory. And in addition, if you have your own trajectory class, you should create it and send back to the tracking manager. Then tracking manager will not create a default trajectory, but use yours. Okay? And also, there are, in particular in high energy physics, there are a lot of use cases. You really want to know from which original particle this particular tiny track come from. Okay? It's really a bookkeeping issue. And so, to make a connection from primary particle to G4 track, you can ask primary particle, get track ID. This will return the track ID that starts from 0, 1, 2, 3. Okay? So it returns the integer. Okay? And in opposite direction, you can ask to the dynamic particle if this particular particle directly comes from the primary particle. If it is the case, it returns a pointer. Otherwise, it returns null. Okay? And use a primary vertex information, primary particle information, track information. You can use these informations to really do the bookkeeping. And here's the example. Example extended round event RE01. Basically, this is a very ultra simplified collider detector. This gray or blue, if you like, part is a tracker. And this yellow part is a calorimeter. Okay? And this example utilizes G4 user track information and region information. First, I tell you how we use the track information. So here's the primary particle. So it remembers track information that this is track ID number 1 and source track ID number 1. Source track ID means it really comes from the interaction point. Okay. Now, here's another primary. So primary track ID 2 and source track ID 2. Somehow by interaction, this guy generates a delta ray or secondary, whatever. This is not a primary track, as you know. So it remembers this primary track ID 1, so that it remembers it still comes from this guy rather than that guy. And this source track ID is the track ID of this particle, okay? Until it comes to the entrance of the calorimeter. Here's another delta ray, let's say. This to remember, this anyway comes from this guy, original particle, okay? And here's track ID number 4. Now, this comes to the entrance of calorimeter. It generates shower. Here, all whatever the tiny EM shower or whatever shower particle, they all remember primary track ID is 1, and the source track ID that tells you the particle ID, track ID, which the enter to the calorimeter. Okay, so in this case, it remembers. Originally, it come from here, but actually it comes from here. It all remembers. And even if you have overlaps for each step, each energy deposition, you can create each energy deposition. You can really get this energy deposition come from this guy or that guy. Okay, so in the end, this example has a Higgs decays into 4 muons through a pair of the Z0. So here is Higgs. Here's Z0. Here's the mu plus mu minus. So this is a primary particle information. It says this particular muon turned into track ID 6782. Okay, and it says trajectory of this 6782 is here and such. So it goes through such positions and generate tracker hits such and such. And here the calorimeter hits originated from this track. That means all these energy depositions are not only come from this muon, but whatever the secondaries, delta rays or EM showers, they all are accumulated. But they all come from originally from this muon. Okay? So I invite you to this example. It really tells you how to bookkeep all this history. Okay? And in addition, it also utilizes region information. This is your information, so you implement. In this case, it has 3 booleans. Am I a world volume? Am I a tracker region? Am I a calorimeter region? It said yes or no. So when you create this information and associate to the region, you just set the Boolean value. When you set this information to the tracker region, you just set false, true, false. Okay, simple thing. But this is important, that one of the biggest waste, in particular in a large-scale simulation, is in the sensitive detector or stepping action, you check the volume name to what is the nature of this volume. Okay? For the case of Atlas, each volume has 40 character long or longer. Okay? So every time, every step, if you want to say which volume is it, you have to manipulate 40 characters. It's a really big waste. But instead, you can go to the step to order through the chain, but they order a point access. It's fast, and get this region information. Just ask, are you a tracker? Yes or no. Okay, this is 1,000 times faster. Okay, and it happens every step. So here, use a stepping action. Although it looks like really messy, but starting from the step, get press step point, and just a pointer, and you get the region information for press step point. Again, starting from the step, post step point, and region information. And here, if the press step point is not the calorimeter, here's the exclamation mark, and the post step is in the calorimeter, it means you are getting into a calorimeter. Okay, that's it. So we often need this information. We want to identify when it particularly gets into the calorimeter. Okay, and to do this, don't check the volume name, but use this mechanism. Although code look like messy, but actual operation is just ultra fast. Okay, just pointer access and Boolean operation. That's it. Any question? When you really need this, you come back. Just you remember, not how, but here's the information. Okay? And again, this is the example. Okay? Now, fast simulation, also known as the shower parameterization. Okay, this is something that if there is a calorimeter, if electron comes in or gamma comes in, there will be a big shower. Okay, and it takes a lot of CPU time to generate all the tiny electron that are gamma, positron shower. But almost always, in particular for electromagnetic shower, the shape is the same. Okay? So we can do something better. So here's a kind of animation. So parameterization often takes place along with the envelope. Envelope is typically the mother volume of the module. Okay? In this case, this is a sampling calorimeter. So this envelope is the mother volume. Okay? And for example, for the case of muon, you don't want to parameterize. You really need everything. But if electron comes, instead of generating ultra tiny granular shower, you may sample the spot and deposit energy. Okay? That could be faster. Okay? This is the idea. But even if it's electron, if it comes to rather nasty place, like an edge or the gap, you may not want to parameterize. Okay? So it's really up to you to decide if you want to do sharp parameterization or not. So the idea is the following, or design is the following, sorry. The logical volume, the mother, can be a region, and with to each region, you may specify first simulation manager. Okay? And this first simulation manager can take models, how you parameterize. Model for electron, model for pion, so on and so forth. Okay? And here's the animation. It took more than 2 hours to make this particular single slide. It's animation. Okay? So here's the track. It has a process manager, depending on for each particle type, and it has a transportation, whatever the multiple scattering, whatever the process. And so if you want to do a sharp parameterization, you have to have fast simulation manager process. Stupid name, but this is the name. This is a process. Then, when particle comes, this track comes to the boundary or envelope. This guy check if this is the envelope. And if it's the envelope, then this guy asks if there's any model that could be applied to this particular particle type. Okay? If exists, at the beginning of a step, it's parameterized like this. If this is, for example, muon, then there's no muon model. If that is the case, it goes as is. Okay? It works this way. Okay? So, for example, CMS got a big boost by this sharp parameterization. They are using it, while Atlas failed. The problem of or success of CMS is CMS has a crystal calorimeter. So geometry is very simple. So randomizing energy spot is easy. For the case of Atlas, they have ultra nice, complicated accordion calorimeter. So if we randomly generate spot, it's really costly to locate each point randomly generated that may belong to the cathode, anode, or whatever. So because of this computing overhead, Atlas actually once tried to use this shower parameterization, and it was slower than real simulation. So I'm insisting them to think about use parallel world, where for EM shower particles they see just a bulk averaged material. Then, like CMS, they will get performance. They will get speed. They are discussing forever. Atlas is 5,000 people. They never converge. So this is shower parameterization. Any question? Okay. So this is my most favorite topic. Okay. And actually, this is my idea of more than 30 years ago. I proposed this to the famous Rune Brun, who was in charge of Geant3. He said, wow, this is a nice idea, but it's too complicated to implement. So I said, okay, then I put it in Geant4. Here it is. Okay. The idea is very simple. By default, Geant4 had 3 particle stacks. No other simulator, Geant3, of course, Furuka, MCNP, X, they have only 1 particle stack. Okay? The idea is just very simple. We have 3. Okay? And you can increase number of stacks as many as you want. Okay? Each stack is very simple, exactly similar as Furuka or Geant3, last in, first out. Okay? The idea is the following. We have 3 stacks. Each stack is a simple last in, first out. And it's your method of use the stacking action to classify to which stack you want to store the particle. Okay? And by default, all tracks go to the urgent stack. And keys, track is always popped up from the urgent stack. Okay? And once urgent stack becomes empty, all tracks in the waiting stack are transferred to the urgent stack. Okay? The thing is, for example, simulating EM shower is costly. Okay? For example, for the case of Atlas CMS, what they need is, first of all, primarily they want to discover Higgs. Okay? So Higgs golden signal event is 4 muons. So you want to simulate all these 4 muons that goes to the muon detector. Otherwise, this event is junk. Okay? So in an ordinary simulation, if you shoot fast muons, it spits out a lot of delta rays. Then, given it a fast in, last in, fast out, the second track that is simulated is the delta ray. Okay? And second, third, fourth generation. So before you come back to the next muon, you have to spend a lot of CPU time to simulate stupid, slow electrons. But with this trick, you put all 4 muons to the urgent stack, whatever else to the waiting stack. Then you simulate muon first, then muon, muon, muon. And if these 4 muons don't go to the muon detectors, abort the event. Okay? This is the idea. So here's an animation. Here's the event manager. It gets the event, primary event. Okay? And here's the stacking manager. Here's the tracking manager. Here's your stacking action. Okay? And we have 3 stacks. When event starts, primary tracks come. Each primary track is sent individually to the stacking manager and ask your stacking action to classify. Depending upon your classification, it goes to the stack, waiting stack, or postpone stack, okay? Or deleted. Okay? Then, only from the urgent stack, a particle is popped up and sent to event manager. And event manager will send this track to tracking manager. And of course, tracked. After finishing this track, secondaries come back. For each individual secondary, it's sent to the stacking manager, and stacking action to say it should go to urgent, waiting, postpone, or you don't care. Okay? Once you say you don't care, track is deleted. But be careful. In this case, it's really vanished out from memory. So you lose energy out of that particle. Okay? Okay? Then, of course, pop comes from here again. And sometime later, while we repeat this process, urgent stacks becomes empty. Okay? Then waiting stack is transferred. Then stacking manager tells you that we are now proceeding to the next stage of the simulation. Then if you want, you ask reclassify. If this is requested, this urgent stack is transferred to the temporary stack and pop one by one, you classify. So you sort out once again. Then only from the urgent stack it popped up and go and processed. And further go, urgent stack, waiting stack, both become empty. Then event is over. But we still have something here. That is postponed to the next event. So when next event comes, this is transferred to the urgent stack. Okay? So this is the scenario. So user stacking action. This is the action class we never touched until now. The classification, classify new track is a method. This is track object that is pushed into the stack. So you say you want to put it in urgent, waiting, or postpone, or you don't care. Okay? So this is invoked every time a new track is pushed into the stack. Okay? And once urgent stack becomes empty, all the tracks in the waiting stack are transferred to urgent stack, and this method is invoked. So if you want, you can say, I'd like to reclassify. Okay? And this one is invoked at the beginning of the next event, so that you may reset the criteria. Okay? So there are many interesting use cases. For example, classify all the secondaries as waiting until reclassify is invoked. Then you can simulate all the primaries first before being bothered by secondaries. Okay? And you may classify the secondary tracks below certain energy as waiting until reclassify is invoked, so that you can roughly simulate the event before being bothered by tiny electromagnetic shower. The third one, you may suspend the track on its fly. Then once particular track is suspended, it's sent back to the stack. And then all the secondaries generated along this particular step is also sent back to the stack. But given stack is lasting first out, the particle popped out next is the secondary. This is essential for optical photon cases that scintillator or Cherenkov. You just suspend per each step, push it back, along with all the secondaries that it got optical photons. Then you simulate these optical photons first to limit the number of the optical photons kept in the memory. Okay? Suspend all the tracks that are leaving from a region and classify the suspended track as waiting. Okay? This is quite useful, in particular for medical application. That suppose you simulate my body. Okay? It's CT scanned. There are box cells, quite a huge number of box cells. It may eat up all the memory, and you don't have enough memory for that. In this case, chop my body into blocks, okay, and load associate region per each block, and read the CT scan data only for this particular block, and simulate everything. And if particle goes out, put to the stack associated to each other region. Okay. If this region becomes empty, go to the other one, so on and so forth. Of course, if you move to the next region, you have to read the new CT scan data for this region. This is essentially very useful if the number of boxes is too huge compared to the number of particles you have to store. Okay? It's a memory competition. Okay? For this use cases, we allow the user to add arbitrary number of stacks. Okay? So, for this third case, here's a sample. In a user stepping action, you get a track. If track is something, then just you set the track status suspended. Then, please, here, if particle is suspended, track is suspended, it comes back here, and with all the secondaries. And suspended track comes first, and followed by all the secondaries, then pushed. So in this case, you don't need to do any trick here. Just they all go to the urgent stack. But given the order, next one to be popped up is the secondary. Okay. So RE05 reads basically the Higgs event, and it really utilizes this kind of stacking mechanism. So this has a ultra simplified collider detector, tracker, calorimeter, and muon. And it has Higgs event that Higgs decays into 4 muons. So what you really care is you really want to know, first of all, these 4 muons really go to the muon detectors, right? So only the primary muons are pushed into the urgent stack, while all other primaries and all secondaries are pushed into the waiting stack. So when we start, we have only 4 tracks in our urgent stack. Okay? So one after the other, we simulate. And even if they are delta rates, they all go to the waiting. So that you can check if these all 4 muons go to the muon detector. If it is not the case, you are not interested in this particular event, so you abort it. Okay? The next stage, only the primary charged particles are pushed into the urgent stack. And all other primaries, that means neutral, and also secondaries are pushed in the waiting stack. Then we see all the charged tracks in the tracking volume. Okay? And once particle comes to the entrance of calorimeter, it's also suspended. And suspended also goes to waiting. With this scenario, you can simulate all the charged particles in the tracking volume, okay, without creating any shower, to see if these 4 muons are clean enough. Okay? And if it is not the case, you abort the event. Then, finally, you create region of interest that close to the muon, and push tracks that are in the region of interest into the urgent stack, so that you simulate showers only in the region of interest. Okay? The idea is very simple. Abort the event at earliest opportunity. Okay? Don't be bothered by shower, for example, unnecessary shower. Or if particles get into the shielding and you never see, that would be the last thing to simulate, even if you have to simulate. In a lower energy case, for example, if you have a better counter, track the particle that is going toward better first. Because if there's better counter hit, you abort that event. The idea is, please, abort the event at earliest opportunity without being bothered by something else. And to do this trick, this stacking mechanism really works. So this is the most clever part of the simulation, I must say. Okay, any question? It's done. Yes?
I don't know if you missed something, but I don't quite understand why you need 2 classifications, like waiting and postpone.
Postpone is, stack is, it is transferred to the next event. Suppose for the Atlas CMS, there are loopers staying in the tracking region forever. In this case, this particle, this track, may arrive in the next beam crossing. So this postpone stack is used only for that kind of use case. So for other use cases, you don't care. Just play with the urgent and waiting. Yes. Or you can really increase the number if you like. You just think about priorities. And in Geant3 or Fluka MCNP, they have just one stack, but it allows you to say priority by double number for each track. But that means every time you pop a track, you have to make a survey to pick up the highest priority. And this is quite costly if you have thousands of particles in a stack. But with this case, just play with the stack, 2 stacks, you're done. That was my 30-year ago idea. Yes. Okay, we get into the lunch break just on time. And actually, after the break, we have a dedicated Q&A time slot. So, of course, you can ask me, Mihari, Dennis, directly any of your questions, but we encourage you to share your question with all the audience, if you can, so that we can discuss. Okay? We have 30 minutes of this such time. Okay? And after this 30 minutes Q&A, we get into the final few informations. Okay, so we start at 1:30, right? 1:30, okay. And if you can just catch us during the lunch break or just after this announcement, so that we can prepare to answer your question. Okay.